We're going to talk about Coulombs Law. Now, here's how you say it. Coo, like he's cool. Ohms, like he's meditating. Or like you're combing your hair. Coulomb. Coulombs. No. Okay, this class is really sad. All right. So, now, here's what Coulomb's Law is all about. And please listen. We all know about static electricity, right? Now, if you ever put your laundry in, well, some of you have never done laundry before, but when somebody does laundry for you, they throw your laundry in the dryer, and then they pull your socks out, and all your socks are sticking together. They have static electricity, right? And ancient people, people long time ago, noticed that you can get a static electric charge. And they didn't know what it was. They had no idea. You guys took chemistry probably, and you know about protons and electrons and stuff like that. But they didn't know about that. But they did have this stuff called, here's a little bit of chunk of amber. Amber. Okay. Sometimes amber is a girl's name. But amber is a semi-precious stone. And actually what it is, it's fossilized tree pitch. You ever seen pitch coming out of like a pine tree or something? If it gets buried or whatever and fossilized, it turns into amber. Now what amber is nature's plastic. It's actually it's a polymer. And it turns out that when you, don't ask me why you would do this, but if you take a chunk of amber or a chunk of plastic and you rub it on hair, like rabbit fur or your own head or whatever, it'll get a static electric charge. Okay? Now the Latin word for amber is electra. And so now Benjamin Franklin, and by the way, we're doing a very abbreviated version of this, and I'd really like you to put your phones down and pay attention to what I'm talking about. Benjamin Franklin, the first great American physicist, he decided that here's what happened. If I have some, maybe I'll draw a little bunny rabbit. Not a very good rabbit, sorry. So I take this chunk of amber and I rub it on this bunny rabbit. Benjamin Franklin thought this is what was happening. That matter is made out of this electrical fluid. All matter has electrical fluid. And that when you rub amber on rabbit fur, the rabbit fur sucks out some of the electrical fluid from the amber. And so the bunny rabbit, the hair, is going to have too much electrical fluid. And the amber is going to have too little electrical fluid. So it lacks electrical fluid. Now, this electrical fluid wants to equalize itself out. And so if you put them close together, you might get a little spark. Have you ever had a little electrical spark happen? Like, have you ever gone down one of those plastic slides on a playground, and then when you step, your hair's all sticking straight up and all that? We're gonna play with that later on. Van de Graaff generator. I'm gonna electrically shock all of you. It's gonna be awesome. Okay. Now, so Benjamin Franklin said this has a surplus of electric fluid, so he called it positive. It's got more than it needs. And then the other one is negative. Now, actually, what's actually happening is kind of the opposite and kind of different. What we know now is this. Matter is made out of what we call charged particles, right? Matter is made out of protons, electrons, and neutrons. Now, neutrons, we don't really care about neutrons for what we're doing. But protons are in, and I'm going to assume that you know what an atom is, you know, the basic structure of an atom. But the proton is in like the center, the middle. Here's a few protons in here. And buzzing around the outside of this are the electrons. And they're in orbitals and, you know, S and P and D and F or whatever orbitals. We're not going to do orbitals, okay? We're not going to worry about that. But this is what, and then we have a few neutrons in there to add some mass. But what actually happens, if you do this at home, okay? This is a lesson for a substitute teacher, so can't do it. But take a balloon, go home, blow up a balloon, rub it on your head, and then you stick it on a wall. Have you ever done that? Yeah. What's happening is that the balloon is actually stripping electrons off of your hair. It's collecting an excess of electrons. And since amber is a plastic and latex for a balloon is a plastic, plastics tend to collect electrons when you have friction. And so you get a surplus. Actually, it's a surplus over here, not a deficit. So Benjamin Franklin was wrong. But the surplus of electrons, well, why do we call them electrons? Well, it's named after amber, electrons. Isn't that cool? All right. And so what happens is that these particles that make up all the atoms that make up everything, all matter, except dark matter, but we don't worry about dark matter. All the ordinary matter that we deal with in everyday life is made out of these three subatomic particles. We have electrons and we have protons. Now, why do we call them plus and minus? That is what Benjamin Franklin came up with. It turns out to be very, very convenient to do that. Now, it turns out that if you have got one single solitary electron and one single solitary proton, they attract each other. Now, don't worry about why. Why do electrons and protons attract each other? Don't worry about why. We just know that they do. Okay, and we're going to describe it. Okay, and notice in the essential question for this, it says, how do we describe the electron? Not why, it's how. But there are electrical forces that want to bring them together. Now, long before we knew about electrons and protons, we knew about electricity. In the 1800s, people like Davies and Faraday and a bunch of Volta and all these people, they were doing all these experiments with electricity. They had no idea what electricity was. They didn't know about electrons or protons. That wasn't discovered, till about 120 years ago by, J.J. Thomson and those people. So, there was a whole bunch of scientists, just right around the year 1900, plus or minus, that kind of discovered what atoms are made out of. And you learn all about that in chemistry, I hope. But if I've got a big basket of electrons, a lot, it would take me probably billions of years at the rate that I'm drawing all these electrons, to create what we call a Coulomb of electrons. Think of a basket. Here's a basket. Just a little basket. I'll put a little handle on it. Okay. A big basket of electrons, and then maybe I have a big basket of protons. And protons, we just draw a plus sign. Well, we define a big mass of charge. We have a quantity of charge, and there's a way of defining it. We're not going to go over that right now. Just to make, you know, you have it like eggs. How do you buy eggs when you go to the store? You buy them by the dozen, a dozen eggs. Well, if you got a big basket of electrons, we call that 1 Coulomb of electrons. Well, and then 1 Coulomb of protons. Now this is the unit we use. Now, but it's a bunch of charged particles that are been pulled away from the other charged particles. They're kind of isolated, all one kind of charge, and all the negative charge, all the positive charge, been separated. Now the amount, the way we measure it is, amount is in coulombs. Well, if you have 1 electron, that's equal to negative 1.6 times 10 to the negative 19 coulombs. And if you have 1 proton, that turns out to have positive 1.6 times 10 to the negative 19 coulombs. Here's something that we've discovered. Electrons and protons have exactly the same amount of charge. Now, why do we call one negative and one positive? Well, there is a difference, okay, between them, in that the electrons and the protons, they want to get together. Now, they can only get so close, and that has to do with quantum mechanics, which we're not going to discuss here. They can only get so close in an atom, depending on what energy level they're in. But they can't actually collapse together. But if you separate them, if you took an atom and you took away all its electrons, those electrons and the protons in that nucleus of that atom, boy, they really want to get back together. And that's why we have chemistry. It's all those electrons getting rearranged and protons wanting them or not carrying, or what, you know, it's all very complicated. So this is a Coulomb of charge. Now the symbol, the variable for charge, so we have charge. The variable name for charge is Q. Now sometimes you'll see it as a lowercase q. Sometimes they'll use a capital Q. It's the only quantity I know of where they kind of, well, sometimes radius. You know, you have the radius of a circle. Sometimes they use little r. Sometimes you use capital R for the radius of a circle. Well, same. And I don't know why they use the letter Q. So don't ask. I don't know. I'm just used to it now. And what are the units? Coulombs. What's the abbreviation for coulombs? You know, like meters. What's the abbreviation for meters? M. What's the abbreviation for seconds? S. So what do you think the abbreviation for coulombs is? C, but it's a capital C. See? So 1 electron equals negative 1.6 times 10 to the negative 19 coulombs. So, they discovered all of this, and you can separate charge, and you can put negative charge on one thing and positive charge on another, and here's what they kind of figured out, which is very cool. And it was a guy named Coulomb who figured this out. So they not only named the law after him, but they named the unit after him too. It's pretty cool. So here's what happens. Let's say I get a big basket of positive charge, and I'll call that Q1. And I get another basket of positive charge. It can be the same amount of charge or more or less, whatever, but it's positive. And I'll call that Q2. Here's what we observe. We observe that they repel each other. I mean, they apply a force. And they push each other apart with the electric force. Well, what if I have a basket of negative charge and a negative charge here? What do? They repel each other. And these forces are intense, by the way. But what happens if I put positive charge here and negative charge over here? What happens? They attract each other. And it is the attraction and repulsion of charges like this that holds matter together, that makes chemistry happen, that makes molecules, do their thing. Okay. So, now, what is this force? Well, this is force. Okay, this is for Kayla and Sean. Sean,
Okay.
I'm recording right now, so I don't want to stop. All right. Well, here's what we have discovered, and Coulomb figured this out. That the amount, we're going to call it F sub E. What does the E stand for? Electric. This is the electric force. F stands for force. E stands for electric. This is the electric force. Well, first of all, it depends on how much charge you have. It depends on how big Q1 is. And it also depends on the other charge, Q2, and it's directly proportional. If I double Q1, I will double the amount of force. If I double Q2, I will double the amount of force. If this is twice as big and this is twice as big, I'd have 4 times as much force. It also depends on how far apart they are. I'm going to call this R. Sometimes books will use D for distance instead of R. I like to use R. It depends on R. The farther apart they are, though, the weaker the force. But here's the thing. If I took these two forces, or these two charges, and I made them twice as far apart from each other, I would only have 1/4 as much repulsion. Because it doesn't vary by 1 over R, it varies by 1 over R squared. It's the square of the distance. If you double the distance between the charges, the force goes down by a factor of 4. You divide by 4. Now, if you make them twice, if you half the distance, you will have 4 times the force. So they really, Now, by the way, anybody remember anything else that does that? Varies by the square of the distance? Yeah? Gravity, yeah. Gravity between planets. Now, this is all you can change. If you've got a little basket of charge here and a charge here, and they're a certain distance apart, all you can do to affect what this force is figure out how far apart they are, or change how far apart they are, and change what the charge is. That's all you can do to affect the force. But look, this is Coulomb squared, and this is meter squared. I want newtons. So what I need is a constant of proportionality that's going to make the units work. Now, remember we had the force of gravity. We had G m1 m2 over r squared. Do you remember that? It's a long time ago. I think it was before winter break. Well, we need the same kind of thing, but we call it K. And here's what Coulomb did. Coulomb solved for K. He took this equation, and he said, all right, here's what I'm going to do. I'm going to say K. And by the way, it's unfortunate, isn't it? We also use lowercase k to represent the spring constant. Okay, card people, you can go quietly, but you're going to need to watch this at home. Shh. Okay, now look. Here's what he did. He took two charges and he actually measured the force between them. He measured the electric force. And then he measured the charge on them. And, well, he also measured the distance apart. And then he measured Q1 and he measured Q2. And he plugged them into this equation. And he got this constant. No matter what charges you use and no matter how far apart you are, when you measure the force and you plug in all your values, you get the same thing. You get this constant of nature. It's called the electric constant. The electric constant. Okay. Now, by the way, if you're using springs and you see a little k like that, it means spring constant. If you see lowercase k and you're dealing with charges and stuff, you're dealing with the electric constant. You just have to know from the context what little k stands for. Sorry. Well, he did the experiment, he plugged in his numbers, and he got this value. 8.99 times 10 to the 9. Now, what units is K going to have? Look at this. What units does force have? Newtons. What does R squared have? Meters squared. What does Q have? Coulombs. Coulombs times Coulomb is Coulomb squared. And this is the electric constant. It is a property of our universe. Our universe has, well, it turns out the force is pretty dang big. Look at this. 8.99, you can also use just 9, right? 9. What does 10 to the 9 mean? Huh?
9 zeros.
Yeah, good. 9 zeros. What is 9 zeros? B. Starts with a B. It's a billion, right? 10 to the 3 is 1,000. 10 to the 6 is a million. 10 to the 9 is a billion. 10 to the 12 is a trillion. Or at least in America. All right. Shh. All right. This is a huge number. If I put a coulomb of charge right here and a coulomb of charge over here, like let's say negative charge, and I put them 1 meter apart, you would have 9 billion newtons of repulsive force. This would be a bad day, 9 billion newtons. This would create almost like an explosion. Where do you need to go? Okay, watch it at home. Ambiance. I don't know why they never asked me to model an ambiance. All right.
Bye-bye.
Oh my gosh. Wow. All the ambiance. The card people have left. The ambiance. Okay, now the people that matter are still here. All right. So this gives us Coulombs Law. The electric force between two charged particles is equal to K, Q1, Q2 over R squared. Now the direction it's in depends on whether you're dealing with positive or negative charge. If you have if Q1 is positive and Q2 is negative, you'll get a negative answer. And a negative answer, when you use Coulombs Law, just means they're attractive. They attract each other. If you get a positive answer, like what, if you have a negative charge and a negative charge, what's a negative times a negative? Positive. And if you get a positive answer, that just means that the forces push each other apart. And they obey this law. And by the way, and here's something amazing, okay? And this tells you, well, first of all, let's compare. Look at big G, right, from gravity. What was big G? Anybody remember? Extra credit for whoever remembers big G off the top of their head. What? What? No, you don't know. Okay, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. I don't know. Did you say that? I couldn't hear you. You're all the way in the back. All right. Now look. Look how tiny this is.
What is
if I put a kilogram of mass and a kilogram of mass 1 meter apart, I get 66 trillionths of a Newton. I'll tell you what, if I put a kilogram of electrons 1 meter away from another kilogram of electrons, it will shred the Earth. I mean, the repulsive force, you would have the biggest thermonuclear, it would be like a supernova going off. Okay, it's the electric force is strong, and that's why you don't fall through the floor into the center of the Earth. Gravity is pulling you down, but you hit the floor. The electron clouds on the bottom of your shoes are hitting the electron clouds of the ground. And that repulsive force between the electron clouds of your shoes and the floor, they're so strong that there's no way you can just fall through. Because atoms are mostly, right? You probably learned that in chemistry. Atoms are mostly empty space. I mean, if I drew the nucleus this big, in reality, if I drew a scale model of it, the electrons would be a couple of miles away. And what's in between them? Nothing. Empty space. Quantum foam. Okay, if you're listening, if you know about that kind of stuff. So the electric force, super strong. Okay, but now, so what you're going to have to do is use this law to figure out what the force is. Now, let's go ahead and do a problem. Example. How much time we got left? 5 minutes. Well, no. We have 9 minutes left. Good try, though. But I'll be done in about 5 minutes. Let's say I've got...
We don't have 9 minutes today, Mr. Lake.
Oh, you're right.
We have 4 minutes now.
We have 4 minutes.
That was close.
Oh, my God.
You can still do math.
Let's say Q1 equals 3 microcoulombs. Q2, this is given. Do this. Q2 equals 5 microcoulombs equals. Have you ever seen this micro before? Yeah, you will. All right. And let's say they are 2 meters apart. So R equals 2 meters. Sorry, this is kind of sloppy, but oh well. Now, given, find the force on Q1. Well, let's solve it. The force between these objects, this is easy, you guys, it really is. Now, punching it in your calculator is kind of hard. F equals K, Q1, Q2 over R squared. This equals 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Am I on screen? Oh, yep. Then, what does micro mean? This is 3 times 10 to the negative. Micro means negative 6 coulombs. This is 5 times 10 to the negative 6 coulombs. Divide by 2 meters squared. Now, you're going to have to punch that into your calculator, and you'll get the answer, but we're out of time. Do that, and then notice which direction is Q1 going to be forced to move? Or what's the direction of the electric force? To the left or to the right on Q1? You got a 50-50 chance. You might as well guess. Left. Left! Yes, left. Good job. Why is it to the left? It's repulsive. They're both positive, so they're pushing each other away. That is all. Good luck with your homework. It's a little bit harder than what I've got. Good luck.